Alright, so welcome to our very first class in Phys 101, another level physics. Okay, so in today's class video, we are going to cover a lot. At first, we will talk about physical quantities, then we move to dimensions as well as applications of dimension. Then finally, we move further to conversion factor. And as you can see, measurement and unit is the very first chapter in physics 101. Please take note that this physics, or this course rather, is an 100 level course. Okay, so at first we will start with physical quantities, and I believe that you guys know physical quantities. You guys have heard of fundamental quantities and derived quantity once, yeah, if not even once, many times when you guys were still in your own level. Okay, so let's kick straight to the video. Now, physical quantities, there are two types of physical quantities. We have the fundamental quantities as well as the derived quantities. Now, what are fundamental quantities? Fundamental quantities, they are basic quantities. Okay, they are basic quantities in which all other quantities are gotten from. Okay, so the important thing you need to take note here is that fundamental quantity, they are basic quantity in which other quantity are gotten from. And note, fundamental quantity, they are what? They are 7. Okay, yes, there are 7 fundamental quantities in physics, and they are mass, length, time, current, temperature, luminous intensity, and the last one amount of substance. Okay, amount of substance. Okay, so yeah, just take note that there are 7 fundamental quantities in physics: mass, length, time, current, temperature, luminous intensity, and last one, amount of substance, which we can also call mole. Okay, now move to the next part, which is derived quantities. Now, what are derived quantities? Derived quantities, these are quantities that are gotten from fundamental quantity. Now remember, fundamental quantity, they are the basic quantity in which other quantities are gotten from, right? So derived quantities, these are quantities that are gotten from fundamental quantities. Unlike fundamental quantities that are 7, derived quantities, there are so many. They are gotten when you had 2 or more fundamental quantities together, we get what? You get a derived quantity. So this is why there are very many, because of the addition of 2 or more fundamental quantities. Okay, yes. So this is all you need to know about physical quantities, fundamental quantities, derived quantities. Okay, yes. Now move straight to dimension and what? And its applications. Okay, dimension and its what? And its application. You may ask, what is the meaning of dimension? Dimension just means the heart. Dimension is the heart of representing. Dimension is the art of representing quantities. It's the art of representing quantities using letters like L, T. Okay, yes. So if they ask you, what is dimension? Dimension is just the art of representing quantity using what? L, T. The art of representing quantity using MLT, that process is known as what? That process is known as dimension. Okay, now move straight forward to this part of the board. Quantities and what? And their dimension. Now remember, I told you guys that, there are different type of quantity. We have fundamental quantity, and we also have derived quantity. Now, when all these quantities, when we represent them, when we represent those quantity using letters such as MLT, please, it's MLT only. Okay, so when all those quantities such as fundamental quantity, derived quantity, and all those quantities, when they are represented using letters, that present as what? That present as what? Dimension. So in this video, I'll teach you guys how to look for the dimensions of some quantities, because they usually ask you in your 100-level first semester exam. Okay, so let's continue. Now, if you look at this part of the board, see quantity and you see dimension. Now, mass is a fundamental quantity, length is a fundamental quantity, time is a fundamental quantity. Now, what is the dimension for mass? Dimension of mass is what? Capital letter M. Dimension of length is capital letter L. The dimension of time is what? Capital letter T. I don't know if you understand. Now take note. Take note. Fundamental quantity. Fundamental quantity. Fundamental quantities dimension is a single letter. Is a single letter. Okay. Yes. If you look at these quantities here, they are fundamental quantities. Okay. And if you look at the dimension is also made up. It's only made up of what? One letter. Look at mass. Dimension of mass is capital letter M. Dimension of length is capital letter L. Dimension of time is capital letter T. I don't know if you understand, because they are what? Fundamental quantities. Okay. Fundamental quantities dimension is a single letter. But for derived quantities, their dimension is not a single letter. It's made up of more than one letters. Okay. Yes, this is because derived quantities are gotten when we add two or more fundamental quantities together. Okay. Yes. Now, let me teach you guys how to look for the dimensions of some quantities. Now, before we start looking for the dimensions of particular quantities, you need to have an idea of indices. And if you understand, if you look at the board there, I already give you guys 3 laws of indices, but there are about 7 laws, but we're not doing maths. Okay, so that is why I'll give you guys 3. These 3 laws will help you to look for the dimension of any quantity in physics. Okay, now before I move straight to the law of indices, you guys should focus here. There's something you guys focus here. There's something I want to tell you guys. Now, if you look at it, you look at some quantity here: length, breadth, height, altitude, distance, displacement, and what? And depth. Now, take note. Take note. Remember, why is the unit, the SI unit for? Where is the SI unit for length? We all know that the SI unit for length is what? Is meter, right? Is meter. The SI unit for length is meter. Why the dimension of length is what? Is capital letter L, right? Yes. Now, if you look at the board, look at this quantity: breadth, height, altitude, distance, displacement, and depth. Please take note. All these quantity, they have the same dimension as what? They have the same dimension as length. The reason is because they also what? Because what? Because their SI unit is also what? Is also meter. So this is why they also have what? The same dimension as what? As length. So if they ask what is the dimension of breadth? Dimension of breadth will be what? Capital letter L. What is the dimension of height? L. Altitude L. Distance L. Displacement L. Depth L. Okay. Yes. This is because the reason why they have the same dimension as length is because they have the same SI unit as what? As length. Okay. Yes. I'm not going to dive into SI unit because that is for O level. Okay. Yes. So let's continue. Now, how do you look for the dimension of a particular quantity? How can I look for the dimension of a particular quantity? At first, I will go back to this place, okay? Now, how do you look for the dimension of a particular quantity? At first, know the formula of that quantity. Know the formula of that quantity. This will help you. If you can know the formula of that quantity and you know the law of indices, you can easily get the dimension of what? Of such quantity. Now, let's move back to this place. The laws of indices. Now, let me break it down. This very first law, which is known as the product law, it states that when the same base, when they are multiplying each other, we pick one of the base, we take one of the base, and we do what? We add their power. Okay. Yes. When they are multiplying each other, we take one of the base, then we add what? Their power. So, for example, let me give you guys an example. Area is made up of length times breadth, right? Yes. Now, what is the dimension of length? Dimension of length is L. Dimension of breadth, I told you guys, is still what? Is still L, right? Now, this L standing alone is still something as L raised to power 1. Yes. L standing alone is still something as L raised to power 1. Anything raised to power 1 is we still give it that same thing. I don't know if you understand. B standing alone is still something as what? B raised to power 1. Okay, it's the same thing. Means that B is just 1, like just B. Okay. Yes. Now, let's go down to this place. Look at these two base. If you look at these two, they are the same base, right? L, L. They are the same base, right? So what are we now? Because all these laws of indices is applicable when getting dimension of some quantities, okay? So let's say for A, let's use area for an example. Now, area is number of length times breadth. And what is it? There is dimension of length. Dimension of length is capital letter L. Dimension of breadth is what? Still capital letter L. I've explained that to you guys, okay? Yes. Now, this same thing, this one is still the same thing as this, okay? Yes, L is power 1, L is power 1, okay? Yes. Now, what does the very first, what does the first law of indices say? It said that when the same base are multiplying each other, we will do what? We take one of the base and we will do what? We add their power 1, okay? If you add 1 plus 1 give us 2. So it might be what? L2, okay? So this is just an example of what I'm saying, okay? Yes. So this is the very first law. We said that when the same base are multiplying, it might not only be 2, it might be even 3, okay? Now, even be theory. Let me put A here, for example. Yes, when the same base, when they are multiplying each other, we will take one of the base and we'll do what? We will add their powers, right? Yes, we will add their powers. Okay, so this is the very first law. Now, what about the second law? The second law is just quite the opposite. When the same base, when they are dividing each other, what do? We will take one of the base. Look at this law. When they are dividing each other, we take one of the base, then we do what? We subtract their power. Yes, we subtract what? We subtract their power. Okay? Yes. Don't worry, you guys will see the application soon, okay? Yes. Now let me go to the very last law. Now the very last law, okay, which is a raised power minus n equals to what? Now, when a base is raised to power a negative number, and when a base is raised to power a negative number, it's still the same thing as what? It's still the same thing as 1 over a raised to power the number. I don't know if you understand. When, for example, when a base, let's say 5 is the base, right? When a base is raised to power a negative number, let me use minus 2 here, okay? It's still the same thing as what? 1. This minus you do like this, then we'll bring out the base, then the power, right? Yes, so this one is still the same thing as this. I don't know if you understand. It's still the same thing as what? This. Now, it's also applicable to something like this. 1 over L. Okay, I'm coming. L raised power minus 1. L raised power minus 1 is still the same thing as what? It's still the same thing as 1 over L raised to power what? Raised to power 1. Remember, L raised to power 1 will still give us what? We still give us L, right? So this one is still the same thing as what? This, okay? So please take note of these 3 rules, okay? Because they are very, very applicable. We are going to use them while getting the dimension of what? Of some quantities, okay? When the same base, when they are multiplying each other, we take one of the base and we add their powers. When the same base, when they are dividing each other, we take one of the base, we subtract their power. Then when a base is raised to the power of a negative number, when a base is raised to the power of a negative number, it's still the same thing as what? 1 over that base raised to power the number. I don't know if you understand, okay? Yes. Now, let's look for the dimension of what? Of some quantities, okay? Yes. Now, what is the first thing I tell you? In order to look for the dimension of a particular quantity, at first you need to know the formula of that quantity. Now, let me start with area. The area resistance is equal to what? It's equal to, the formula is length times what? Length times breadth, okay? Now, remember, I told you guys that for a metal quantity, they only have their dimension is just made up of a single letter. So if you look at its mass, the dimension of mass is a capital letter L, dimension of length capital letter L, dimension of time is capital letter T, okay? It's just made up of one letter. But for derived quantities, their dimension is made up of more than a single letter. It's made up of more than one letter. I don't even understand, okay? Now let's look for area. Area is equal to length times what? Length times breadth. And what is the dimension of length? Dimension of length is capital letter L, okay? Then times. Now what about breadth? What about breadth? Now that I told you guys that breadth has the same dimension as what? As length. So it's still capital letter what? L, okay? L standing alone is still something as what? L raised power 1. The same thing, L raised power 1. Now according to the very first law of indices, when the same base are multiplying each other, we take one of the base, we will what? Add their power. So raised to everything will be what? L raised power 2, right? So the dimension of area is what? L raised to power 2. Now let's use another fundamental, another derived quantity, volume. What is the formula for volume? Formula of volume is what? Is length times breadth times what? Times height, right? Yes. What is the dimension of length? Is L. What is the dimension of breadth? Is TL. What is the dimension of height? Is TL. I told you guys earlier, right? Yes. Now this one is still the same thing as what? It's still the same thing as L raised power 1, L raised power 1, L raised power 1, right? Yes. What does this very first law tell us? Told us that when the same base, when they are multiplying each other, we take one of the base, then we add what? Their power 1 plus 1 plus 1, everything will be L raised power 3. So this is the dimension of what? Of volume. Now let's dive deeper. Now we move straight to what? Dimension of what? Velocity, right? Yes, dimension of velocity. Okay. Now at first you need to know the formula of that point. Where is velocity? Displacement over what? Displacement over time, right? Yes, displacement over time. Now what is the dimension of what? This is how you can look for the dimension of velocity. What is the dimension of displacement? Dimension of displacement is capital letter what? Capital letter L, right? Over what is the dimension of time? Dimension of time is capital letter T, right? Yes. So this is dimension of what? This is dimension of what? Velocity. Now this one is still the same thing as what? It's still the same thing as LT raised power minus 1. The third law. LT raised power minus 1. Let me break it down for you. Now LT raised power minus 1 is the same thing as L times T raised power minus 1, right? Yes. Now look at this part, T raised power minus 1. T raised power minus 1, let's see almost something like this, right? Yes, T raised power minus 1 it's the same thing as what? It means that 1 divide T, then raised power what? That one, that is the third law. Then what the third law of indices said? That it said that when a base is raised to the power of a negative number, it's still the same thing as what? 1 over that base raised to power what? Their number. Yes. So if this is still the same thing as this, everything here is still the same thing as what? T raised power 1 will still give us T. So this one is still the same thing as what? 1 over what? 1 over T, right? Yes. Now if you multiply it with length, if you multiply it with length, we arrive with what? L raised power T. We arrive back to this place. I don't even understand. So that's to tell you that L T raised power minus 1 is still the same thing as what? It's still the same thing as L over T, because T raised power minus 1 is the same thing as what? 1 over T raised power what? 1. Yes, if you multiply this with length, we get back what? Get this one back, right? So that is just it, okay? So what is the dimension of velocity is what? Is L over T, or you can also say L T raised power what? Minus 1. Yes. Now let's move further. Let me just do 2 other quantities, then we move to conversion factor, which is very, very important. Okay. So we all know that dimension of velocity is what? Dimension of velocity is L T raised power minus 1. Now move to let me give you another quantity, acceleration. Now at first you need to know the formula of the quantity. Acceleration is what? Acceleration is equal to what? Velocity over what? Time. Now the same should look for what? The dimension of acceleration. What is the dimension of velocity? Dimension of velocity is what? Is L T raised power minus 1, right? Yes. Dimension of time is still what? Is capital letter T, right? So we arrive with what? L T raised power minus 1 all over what? T. Yes. Now if you look at it, T is standing alone. It's still the same thing as what? T standing alone is still something as T raised power what? T raised power 1, right? Yes. Okay. Now, if you look at the second law of indices, we state that when the same base, when they are dividing each other, we will take one of the base and we'll do what? We'll subtract their power. If you look at these two guys, they are what? I mean, when two bases are dividing each other, right? Now, if these two bases, they are what? These two bases, they are the same base, right? Yes, they are the same base, and they are doing what? They are what? Dividing each other, right? So what are we going to do? We will take one of the base and we will subtract what? Their power, right? So if we take one of the base, L, then T, we take one of the base, which is T, we'll do what? We subtract. We subtract. Now, the power of this one is -1, right? The power of this other one is what? It's just 1, right? Yes, it's just 1. So what are we going to do? We subtract what? We subtract their power, right? Yes. So we take one of the base and we subtract their power. -1 -1 will give us -2. So this is the dimension of what? Acceleration. L T raised power -2. Okay, yes. So in summing to everything, this you just need to understand the three laws of these first three laws of indices. If you understand these first three laws, you can use it to solve any dimension. Okay, yes. Okay, so this is the dimension of what? This is the dimension of acceleration. Let me just do one more point. Dimension of force. Remember, I told you guys that you need to know the formula of force. Force is what? Mass times what? Mass times acceleration, right? What is the dimension of acceleration? Dimension of acceleration is what? L T raised power -2. Whatever is dimension of mass? Dimension of mass is what? Capital letter M, right? So if you multiply everything, we land with what? M L T raised power -2. So this is dimension of what? This is dimension of force. Okay. So in summary to everything you have been doing since, I talked about physical quantity, that there are two types: fundamental quantity and derived quantity. Please in unit, let me just be specific. In unit then 100-level exam, they will hardly I've not even seen, they will hardly ask you definition. Yes, it's more of phase 101 is more. I think 80%. No, it's not even 80, 95% calculation, right? It's 95% calculation. So don't expect don't expect definition. You're not asking definition. So that is why I didn't even tell you guys anything about definition. Okay, so we all know fundamental quantity in your whole level, that fundamental quantity, they are what? They are basic quantity. Each other quantities I got it from. We know what is the derived quantity. There are different types of derived quantity. Okay, so yes, there are different types. So these are you look for a dimension of quantities. You know the laws of indices. You know the formula too, right? Yes, fundamental quantities, they just have what is their dimension is just made up of a single letter. Whereas for derived quantities, their dimension is made up of more than one letter. Yeah, so these are all important you need to know about dimension of physical quantity. Now let's move to the this part is very important. It's even more important than this part. No, before then, I forget something. Application of what? Application of dimension. Yes, application of dimension. This is very important. This is very important. Application of dimension. Now, what is all about dimension? Where is the application of dimension? Now, the application of dimension is that dimension enable us to know whether an equation is true or not, or is correct or not. I don't know if you understand. And dimension just tells us whether an equation is correct or not. Let's dive deeper. Now the very first law of equation of motion, the first equation of motion is V equals to U plus AT, right? Yes. What is the application of dimension? Application of dimension is to tell you whether if this equation is correct or not. If this equation is correct, you will know with dimension. If it's not correct, we also know. So how do you bring about dimension analysis? Now, how do dimension tells us whether this formula or whether this equation is correct? Now, an equation, take note, an equation is dimensionally correct when the left-hand side has the same dimension as the right-hand side. I don't know if you understand. When the dimension this side is the same thing as the dimension this side, that's when you know that an equation is correct dimensionally. Yes, that's the importance of dimension. Dimension tells you whether this equation is correct or not. And the equation that is correct, we have the same dimension both in the right hand side and the left hand side. Now let's prove whether this equation is correct. Now, what is the dimension of velocity earlier? The dimension of velocity, we all know that we have solved it right now. I mean, before. Dimension of velocity is what? L t raised by what? Minus 1, right? Yes. Now, this u, which is initial velocity. What is the dimension of initial velocity? Initial velocity is still the same thing as what? It's still the same thing as velocity, right? So it's still what? L to the power minus 1. Then plus, remember, I did dimension of acceleration. Dimension of acceleration is what? L to the power what? Minus 2, right? Yes. Then times, what is the dimension of time? Dimension of time is capital letter what? T. Now, T is standing alone. It's still the same thing. It means what? T raised to power what? 1, right? Yes. So this sentence is still what? T raised to power 1. Yes. Now, if this part, if the dimension in this part is the same as the dimension in this part, we know that this equation is correct. Okay. This is Universe favorite question, and there are many. Okay. So now this place looks familiar. I don't even understand. Look at the very first law. When the same base, when they are what multiplying each other, we take one of the base, then we'll do what? We add their what? We add their power, right? So when we add the power of minus 2, then plus what? 1. We will arrive at minus 2 plus 1 will give us minus 1, right? Yes, minus 2 plus 1 will give us minus 1. So everything here will be what? Will be L to the power minus 1. I don't need to understand. Let me break it down. T raised to the power minus 2 times T raised to the power of minus 2, then times T raised to the power 1. According to the law of indices, we take one of the base, then we'll do what? We add their power. If we add their power, we arrive at what? T raised to the power minus 1. Yes, we arrive at T raised to the power minus 1. Minus 2 plus 1 give us minus 1. So that is how we get. That is everything here. Now, if you look at these two, they are the same, right? Yes. Okay, our normal mass, L plus L. Okay, normal mass will give us what? 2L, right? Yes. Normal mathematics. L plus L will give us 2L, right? Yes. Okay, A plus A will give us 2A. Normal mass, right? Yes. Look at these two, they are the same quantity, right? They are the same. L to the power minus 1, L to the power minus 1. If you add them, what will they give us? They will give us what? 2L to the power minus 1. Normal mathematics. I don't even understand. When you add the same thing together, I can't do the same. You can easily add the same thing. A plus A will give us what? Will give us 2A. I don't know if you understand. B plus B will give us what? 2B. Because they are the same thing. Yes. Okay. So L to the power minus 1 plus A to the power minus 1, they are the same thing, right? So give us what? 2L to the power minus 1. Yes. Now if you look at this place is what? L to the power minus 1. This place is what? 2L to the power minus 1. Now please take note. Important you need to know is that take note is very, very important. Values or figure, they don't have dimension. Okay? Values don't have dimension. Okay? Please, this is very important. Okay, very, very important. Values don't have dimension. Very, very important. Okay. So since 2, which is a value, does not have dimension, we can easily just cancel this. Yes. Okay. So you will see that we arrive at what? L to the power minus 1, L to the power minus 1. So that's to tell you that this equation is what? Is dimensionally correct. This dimensionally or non-dimensionally is correct. This to show that this equation is correct. So these are the applications of what? Of dimension. Okay. So let me I think I should do 2 questions from your textbook. This one particular question in your textbook. And let me do another question in your phase 101. Alright, so if you look at the board, you find 5 questions here. And these questions, they are from your textbook. The exercise question at the back of your textbook, okay? So I only pick as the question that is related to dimension, right? Yes, because we are going to solve all the exercise question. Now, from question 1 to 4, they were asking us if these equations, whether they are dimensionally correct or not, okay? Yes, while the last question, which of the following has the same dimension as what? As time, please. These exercise questions from Uniben past from Uniben textbook, they are usually repeated in their exam. Okay, so take them serious. Okay, now this first question. X, whenever you see X, ox is something as distance, okay? Distance X, okay? It's something as distance, okay? So don't get confused when you see X, it's something as distance, right? Now, they're asking us if X is equals to what? V over 2A, A is acceleration, V is velocity, we know that, right? Yes. Now, is this equation correct? Now, what did I tell you guys? I told you guys that an equation is dimensionally correct when the left-hand side, when the dimension in the left-hand side and the dimension in the right-hand side, they are the same. Yes, when they are the same, that is when you know that the equation is correct or not. Okay? Yes. Now, this side is what? Is x, which is distance, right? Yes. Now, if we look for the dimension of, what is dimension? What is dimension for distance? I told you guys that dimension of distance has the same dimension as what? As length, right? So the dimension of distance is what? Is capital letter what? It's capital letter L, right? Yes. Now, if we look for the dimension, the total dimension here, and it's the total dimension that we get is L, we know that this equation is correct. But if we don't arrive with L, you know that the equation is not correct. Okay, so let's start. Okay, now what is the dimension of velocity? The dimension of velocity is L t raised to power minus 1, right? Yes, remember I told you guys that values, values of figures, they don't have dimension, so we can easily neglect that too. What is the dimension of acceleration? The dimension of acceleration is what? L t raised to power minus 2, right? Yes. Now, if you look at this here, we have arrived at where? We have arrived at indices. Yes, we have arrived at indices. Now let's start with this one. Let's start with this. All right, we have arrived at indices. Okay, so when the same base, this, okay, let me just go through the point. Can easily cancel this one. Yes, let's just go through the point. Okay, can easily cancel this one. Then we're left with what? T raised to power minus 1 all over T raised to power minus 2. Now, according to indices, when the same base are dividing each other, we do what? We subtract their power, right? Yes. So we take one of the base, then we subtract their power. Minus 1, then minus what? 2. Minus 2 give us is what? Is plus 2, right? Yes. So minus 1 plus 2, that will give us 1 now. Abi? I'm not mistaken. That'll give us 1. Let me check. God. What is wrong with me? Minus 1 plus 2. Yes, that'll give us 1. So our total dimension here is what? Is time. So that has to tell you that this equation is not correct, because dimension here is what? L. Dimension here is t, so it's not correct. So number 1, the dimension is not, this equation is not dimensionally correct. Now let's check number 2. Now move to question 2. Which of this equation is dimensionally correct? Is this equation dimensionally correct or not? Now remember, for an equation to be dimensionally correct, the dimension in the left hand side must equal what? The dimension what? In the right hand side. Now what is the dimension in the left hand side of this equation? Remember this is x, and x has the same dimension as what? As length. What is the dimension of length? L, right? So the dimension in the left hand side of this equation is what? Is L. Now let's move to the right hand side. Remember, values don't take what? Values don't have dimension, so we neglect what? We neglect 2. Now let's move to these two other parts, g and t square. Now remember, g is what? G is acceleration due to gravity. And what is the dimension of acceleration due to gravity? Remember, acceleration due to gravity is still the same thing as what? It's still the same thing as acceleration. Therefore, it has the same dimension as what? Acceleration, which is Lt raised to power what? Minus 2. Then times, what is the dimension of time? Dimension of time is what? Capital letter T. Then we put the square. Now, remember, according to the first law of indices, when the same base are multiplying each other, we do what? We take one of the base, then we do what? We add their power. So Lt, we take one of the t, then what we do? We add their power. So minus 2 plus 2 will give us what? We give us 0, right? So anything raised to power 0 will give us what? Will give you 1. So L times 1 give you L. So therefore, the dimension in the right hand side is still also L. So that will tell you that this equation in number 2 is what? Is correct. Actually, Okay, number 3 is still x. So the total dimension here is what? Is L. Yes. Okay. If you look at here, we have this place, this quantity here is L. Okay, is distance is x naught, which is initial distance. Which is the dimension of distance is still L. Now, what about velocity and time? Dimension of velocity is what? L t raised by minus 1. Dimension of time is what? Is t. So if we this one is still something as what? T is standing alone, is still something as what? T raised power 1, right? Yes, T raised power 1. Now, according to indices, when the same base, when they are multiplying short, that we take one of the base, then we do what? We add their power, right? So we take one of the base, which is T, we add their power, minus 1, then plus 1. We get what? Minus 1 plus 1, I think that is 0 now. Yes, so that is 0. So everything here will be what? Everything here will be 0. Abi? Yes. Any t raised to power 0 will give us what? Will give us 1. Remember, when a raised to power 0 give us what? 1. I think that is still indices. Yeah, that is indices. So everything here, this t will be what? Return to what? Return to 1. L times 1 will give us L. So everything here will be what? Everything here will be what? Will be L. Okay? Yes. Okay? Yes. Everything here will be what? Will be L, right? Yes, remember this one is L. Now L plus L will give us what? L plus L will give us 2L. Then this other side is what? L. Remember, not values don't have dimension, so we can cancel it. So that is why that this equation is dimensionally correct. Yes, this equation is dimensionally correct. I don't know if you understand. The equation is dimensionally correct. Okay, so L equals to L. So that is why that this equation is dimensionally correct. Now, what about number 4? What about number 4? Okay, if we look at number 4, v equals to root 2ax. Okay, is this equation dimensionally correct? Now, what is the dimension of velocity? Dimension of velocity is what? L t raised power minus 1, right? Yes. Now, if we solve for the dimension of everything here and we arrive at what? L t raised power minus 1, we know that what this equation is what? Correct. Okay. Yes. Now, okay, yes, okay. So let's break it down because of this one, because of this square root. Let us not affect it, okay? So let's remove the square root. Now, how can we remove the square root? By taking the square of both sides. We take the square of everything. Take the square of both sides. This square we cancel the square root. So we'll be left with v square equals to what? 2ax, right? Yes. So what is the dimension of velocity? The dimension of velocity is what? L t raised power minus 1. Then everything will be what? All squared. Then equals to, remember, values don't take dimension, so we neglect the other one. What is the dimension of acceleration? Dimension of acceleration is what? L t raised power minus 2. Then times dimension of distance is what? Dimension of distance. Remember, I told you guys, it has the same dimension as length. So you see what? L. Okay. Now this said, okay, this one, this is L standing alone, this is something as L raised power 1, right? So this one, yeah, this L standing alone, yeah, this is something as what? L raised power 1. Now, according to the law of indices, we take one of the base, then we add what? Their power. When we add their power, we arrive with something like this. When we add L1 times L1, we arrive with something like this, L1 times L1, right? So we take one of the base, we add what? We add their power. We arrive with what? L2, right? Then plus this other one, t raised to minus 2, right? Yes. Now let's go to this side. Let's go back to this side. This square affects everything. This square affects L. This square affects what? T. So this everything here is still something as what? L raised to power 2, then t raised to minus 1 times 2 give us minus 2. So this is the final answer. This will tell you that this side is the same with this side. This will tell you that, oh, this equation is what? Dimensionally correct. This equation is correct, okay? Yes. So this equation is correct. Now let's move to the last questions under applications of dimension before we move to conversion factor. Okay? Which one of the following has the same dimension as time? Oh my goodness. So we are going to look for each of the dimension. Remember, dimension of time is just capital letter T. So if we look for, we are going to solve for each of them. Anyone we arrive with T, you know that equation, that one is the correct one. Oh my goodness. Let me think. I think I should just fast everything. I cannot just be looking for A, B, C, D, E. Okay. Now let me see. Equations of motion. Remember, equation of motion is V equals to U plus AT. Okay, if in your own private time you can like do it, you can solve for each of them. Whenever you are, whenever when you arrive at t, you know that that one is the correct one. Okay, so we know the equation of motion equals to v equals to u plus at. This is the very first equation. Okay, so if we make this u is initially, let's say 0, so we arrive with v equals to what, at, right? If we make a stand alone, if we make t stand alone, we arrive with v over a. Okay, let me look for which one is v over a. Okay, no one. Okay, let me check. Let me use the other formula. Let me check the other equation of motion formula. I'm just doing this to save time. Okay, let me just do it to save time. S equals to ut plus half at square. Okay, so all here will be 0. U is normal. U is 0 normally. 0 times t give us 0. So I write with s equals to what? Half at square. Okay, so this one is still something else. Okay, um, okay, it will be 2s equals to what? At square, because this 2, because of this half, yes, this 2 multiply this x, so now be 2s equals to 80 square. Okay, so if we make this stand alone, now be what? 2s over a. So if we take the square root of both sides, square root cancel this square, so we arrive with what? Root 2s over a. So b is the right one. I don't want to stress myself, so b is the right one. Okay, now